Okay, so my research area really, there are two threads to it. One is the atomic physics part of it, where I am interested in fundamental atomic processes, like electron interactions or light matter interactions. So this falls into a category, I think Professor Riley mentioned earlier, a few body problems, except he is dealing with nuclear reactions where the atomic physics we're dealing with Coulomb interactions. And we presume that we know these forces, Coulomb forces, very precisely. So few body atomic system lets us test a fundamental understanding of the quantum mechanics. So there's fundamental aspect to it, but there's also applied aspect to it. We also calculate reaction, rates, things like that are useful in, for example, many other applications. So showing here is a electron density distribution in time in this reaction. So you come in with a photon, knocking on helium and freeing 2 electrons. So this is what we call the double ionization process. And as some of you will know, when you talk about the quantum three-body problem, if you look around the periodic table, we know only precisely the solution of the hydrogen, atomic hydrogen. And from helium onward, where you have three-body involved, is still unsolved analytically. So we do this by solving, approximating the time-dependent Schrodinger equation in some way. And so this, by measuring this, electron density distribution as they move outward and compare this with the experiment, it gives us an idea of how, the accurate certain approximations are. So you can see in this picture that basically the inside there's like peanut shaped. So early on the distribution is like dipole, and later on you have 4 lobes developing. We call this quadruple distribution. And the evolution of this tells you a little bit about the electron dynamics. So related is this natural atom, but we also study man-made atom, artificial atoms such as quantum dots. And our research has been on how to treat quantum dot because they have irregular boundary conditions, right? What you're looking at here is like hexagonal regular quantum dot. And this is the wave function of that state. You can already see some complexities in those. So we've been developing some meshless methods to deal with this. And the other aspect of my research is computational physics in general. We can take the techniques that we use in these processes and to study some other problems. In fact, undergrad and grad student can easily relate to that still have significant questions to be answered. So I will show you that there are many such projects where students can get their hands dirty, if you will, getting into research, and but in a familiar setting. So it's really threshold friendly to undergrad participation. So one of the graphs here shows our study of the GR effect. In fact, the precession Mercury. This is supposed to be the sun, okay, the origin, but Mercury, due to general relativistic effect, would actually precess. So we follow the Runge length vector, and we can look at this differential precession. So over here is showing the search for exoplanet. So plot here is basically the wobbling velocity of stars due to a planet around, and it's really by fitting this profile, by searching through data sets, one can figure out, okay, what is the exoplanet mass and things of that type. And it's really amazing that coming from atomic physics, that in this picture, for example, the astronomers can actually measure arc seconds of change, and here they can actually measure speed, you know, of sub-meter per second. So it's really amazing. So to give you an idea, a taste of the type of things I look at, many simulations are posted here. You can take a look at one problem. You know, if it interests you, you know, we can talk further. So I'm picking one here. This is like a double pendulum, right? This is purely classical mechanics, but if you look at the motion of the midsection here, it's fairly regular, but if you look at the lowest tip here, the motion is rather irregular. In fact, it's chaotic, okay? So this has, something to do with chaotic systems, and helium atom, by the way, we believe classically is chaotic, okay? So again, there are many, systems that are familiar yet have significant questions left to be answered. Last, I want to close this with this assimilation. This, in fact, only the last few days, me and my collaborator, we have worked on it. Nobody else has seen it, so we're the first to see this. Okay? So this is a so-called game of life. And you put some rules into how the a neighbor may survive or may become dead, and the simple rules can in fact produce very complicated patterns. So you can analyze this in terms of thermodynamic systems. The beauty of this is that you can actually click on this program, you see how the sausage is made, okay, and you can copy and play with, on your own time here. So I have some graduate student and undergraduate student working with me, and like the speakers before, I always welcome, if you are interested in this, to look into what we're doing or maybe participate.